Okay, in earlier lectures we have seen heat equations solution in terms of conditional expectation. So here we recall very quickly that if f is the initial data and then the expectation of f of wt given w0 is equal to x, this conditional expectation gives a particular function of x, correct, where w is a Brownian motion, and that function of x, if you write down u of t comma x, because this also is a function of t, correct, so u of t comma x, then this function solves the heat equation. So we have seen that, and then what we are going to now ask a very straightforward question, that if my initial data is non-negative, that f is greater or equal to 0, then from this representation it is evident that u should also be non-negative. Why? Because it is after all expectation of a non-negative function of a random variable. So whatever wt value is, positive or negative, does not matter, f of wt would always be non-negative, and then you are taking expectation, that is nothing but an average. So this is greater or equals to 0. Okay. And what we have seen in earlier lectures, that given some kind of conditions on f, okay, so like growth condition, that this satisfies the heat equation. However, the reverse thing we have not established. What is the reverse thing? That given the heat equation, okay, given the heat equation, whether it has a solution, I mean whether you can always write down this as in this form, the solution can be written in this form. Okay, so we are going to ask this question: if we find a non-negative u which solves the heat equation, okay, that is del u del t is equal to half into second order derivative of u with respect to the space x, okay. So when we talk about multidimensional, we write down second order derivative there, Laplacian, correct? Okay, now if we find a non-negative u which solves the heat equation, does u have above type of representation? Okay, so this question we are asking here now, and we are going to answer affirmatively. So this is the Widder's result. So Widder's result is as follows. So let here u be a function on two variables, time and space. So this domain is open interval 0 to capital T, and space is whole R, unbounded domain, and this u is non-negative, so its value is 0 or more than 0. So here the following are equivalent. Okay, so this theorem is saying that the following are equivalent. What are these? That for some non-decreasing function capital F, okay, u of t comma x, this u of t comma x is equal to minus infinity to infinity p of t x y, and then integrated with respect to capital F of y. Okay, how can we do this? Here already we have assumed f to be non-negative or non-decreasing. So non-decreasing functions, for that we can define the notion of Stieltjes integral. So this is just a Stieltjes integral, okay, and then here capital F could be any non-decreasing function. It could be discontinuous function also, like this, okay, like this, that indicator function of close 0 to infinity x, basically Hemiside function, right, that on the positive axis, when x is positive or 0, then capital Fx is 1. If x is negative, then fx is equal to 0. Okay, for such type of functions, it is discontinuous, we cannot talk about its derivative. Okay, it is not differentiable. So this Stieltjes integral cannot be further reduced by dfy divided by dy, okay, into dy. We cannot write down that way. So it is a little different than this type of expression, where we had u of tx is equal to expectation of f of small f of wt. okay, where you can actually write down small f of y dy and ptx dy, okay, because this expectation looks exactly like this, where the same density appears, where I mean like this same density appears, but the function here like small, I mean like you can think this is the antiderivative of small f. But if small f is already a boundary measurable function, then its antiderivative would be continuous. But here we do not have that constraint, so capital F is allowed to be discontinuous even, okay. So this is more general than this setting, okay. So here the derivative of capital F can be using the distributional sense. The distributional sense derivative of capital F is Dirac mass at point 0, correct. Okay, so now the following statements are equivalent. So here I have just written the statement number 1. So statement number 1 is saying that this non-negative function u is written I mean as if just this solves the PD, correct, heat equation, because it looks almost like same but is more general actually. The antiderivative of small f appears as if, correct. So the second condition is that it solves the heat equation, okay. It is not surprising, correct, because of this particular nature it is natural that okay it would solve the heat equation. I mean natural I mean it is not straightforward proof, because we have not proved this for this generality, but for the special case when capital F has a derivative, then this is exactly this, okay. Then we have already proved that solves the heat equation, okay. So this Widder's result says that okay even with this generality this u, okay, would also solve the heat equation, because this is u is classical solution. So it is once differentiable with respect to time variable and twice differentiable with respect to the space variable C12, and del u del t is equal to half del 2 u del x2 on this domain. There is also a third criteria which is also equivalent to these two. What are these? This is for each t positive between 0 to capital T and x real number, u of t minus s ws, okay. So this you can view that as a stochastic process as s runs from closed 0 to open t. I cannot simply put s is equal to t, I cannot make it closed. Why? Because for s is equal to t, this u of t minus t would be 0, u0, okay, and for and then wt, okay. So now u0 here, if you put t is equal to 0, you don't know what would happen here, because here for u0 I can write down, I know that okay w0 is equal to s and it is expression of f of wt, and t is equal to 0 would say that okay f of w0, but w0 is constant, so you can write a small f of x directly. But here you cannot do that simply. Why? Because here you don't have exactly this type of expression, correct. Here so it is because capital F's derivative does not exist, okay, it is this. So I may not have u0 value at 0, I may not have a value, okay. So I cannot have a closed interval t, I can have only open interval t. However, above 0, so in the so like t is equal to 0 is the boundary of the Cartesian product domain, correct, is one boundary part of the boundary, but is not in the interior. So in the interior we can of course define this function u, because and in the interior u is not only defined, it is continuous, it is differentiable, it is it has all the regularity as required to solve this PD. And this process, as s is the time index, okay, when t is fixed, this is a martingale, okay, this is a martingale, u of t minus s ws is a martingale, okay. So how are you going to see this? See, for example, it's like a little backward kind of thing, correct, because here when s is equal to 0, then it is actually u of t comma w0, okay. So let us see this. Imagine that this is my time axis and this is the space, okay, this is the space, So I write down this way maybe. Okay, and at some particular time t, your say you are at some particular point x. So this coordinate is t comma x, and imagine that you are generating one Brownian motion starting from this point, okay, but not as time forwarding but time backward. So this is a say Brownian path, okay, and then you stop at some point, say here t minus s. So basically this distance is s, you go s, so here this direction, okay, and then wherever you stopped, so here you find out this this value u of t minus s ws, okay. So here this coordinate is t minus s, and then what should be it? This height, because it started from here, okay, a Brownian motion, and that Brownian motion here it took exactly s amount of time, so it is ws. Here this position is w0 and is ws, okay, ws, okay. So this point you evaluate the function u, okay. So u of t minus s ws, okay. Now you continue this Brownian motion, I mean s, you continue doing that for each and every s, okay, starting from 0. So here s was 0, starting this, and then what are you going to get? You are going to get a stochastic process, because this function, although this function is deterministic, but the path is random, correct? So you are going to get a stochastic process, and that stochastic process turns out to be a martingale, okay. It is not clear otherwise, correct, because w is of course a martingale, okay, but a function of martingale need not be a martingale. So like w square is not a martingale, correct, but so u is a function of this, correct. But since u satisfies the heat equation, so these things becomes, okay. So it is not true for all possible u, so it is only special for some particular u, and it is saying that these three are equivalent. So am I clear? I mean, could I emphasize that, okay, this third condition also clarify, I mean put some condition on u, okay. So here u is written in this way, all function u cannot be written in this fashion. U satisfies this PD, okay, all functions does not satisfy this PD, for all you may not get a martingale, but okay, these three are equivalent, okay. There is another fourth statement, that u of t comma x is equal to expectation of u t minus s ws, okay. So left hand side does not depend on s, right hand side depends on s, okay. So this is true for all s. So if I fix one particular s, say s is not allowed to take value t, because if I put t, then u of 0 would appear, but I do not have that, correct. I do not have from, I mean neither there, okay. U is also defined only on open interval 0 to capital T, okay. But say u of if s, I put s is equal to 0, then I can check what does it mean. What does it mean? That here the Brownian motion is starting from point x, as I have shown in the picture, and then for s is equal to 0, the w0 would be not a random variable but a deterministic value, that x, and u of t minus 0 is ut. So here expectation of that would be just ut, because this is deterministic. So utx, you are going to get that, okay. So left hand side and right hand sides are equal when s is equal to 0, that we can see very easily. But in general, okay, I mean s is equal to 0 is trivial, I mean that is true for any function u, But in general, for any arbitrary function you would not get this to be true, correct? Because if s is non-zero, then it is not obvious. Okay, so here this part also we can visualize in this, that you fix one particular s, okay, and then you simulate Brownian motion backward direction, maybe a million time. Okay, so another path possibly here, okay, and then evaluate u function at this point. U function is defined on the Cartesian product, right, t comma x. So here, okay, so we have drawn this black and red color, this two paths of Brownian motion, and then there we see that it stopped somewhere, I mean, so at the time point s. And then if we generate such type of millions of paths, okay, and then at each and every for each and every path, when it stops somewhere at some points t minus s comma ws, okay, so there we evaluate the function u, and we are going to get some particular number, correct? We are going to get some particular number, and we take average of that. And here, since our function u is non-negative, so we are going to get millions of such non-negative numbers, and we are going to take average, and that average would be an estimator of expectation of u of t minus s comma ws, correct? And that value would match with the function u at the point t comma x, which was the starting point of the Brownian motion. Okay, so this is the fourth statement that u of t comma x is equal to expectation of u t minus s ws expectation. Okay, so one can find an estimator of this expectation by taking by simulating w say million times, and then finding out that point, okay, and then taking average of those values. Okay, so next we come to Widder's uniqueness theorem. Okay, so we are not going to prove this theorem, we are going to just state this theorem, and while stating, we are going to clarify that where this is different from other earlier theorem. So here let u be a smooth function, that C12 function, once continuously differentiable with respect to time and twice continuously differentiable with respect to space, and it is non-negative function, and u satisfies the heat equation del u del t is equal to half del 2 u del x2. And here furthermore, that at the initial time, if you come close, that t tends to 0 and y tends to x, ut of y, if you find out, and if that value is equal to 0 for each and every choice of x, okay, then the function u should be 0 inside the interior, should be 0 identically. Okay, so in this statement, no growth condition is required on u. Okay, remember that in Tikhonov's theorem we had also another uniqueness theorem with similar conclusion, but there we had to assume that u satisfies certain growth condition, correct? That u of t comma x into is less than or equal to e to the power of ax square for some positive a. So here we don't need such kind of condition. Okay, but however, we of course require u to be non-negative. Okay, you understand that? So earlier u was allowed to be positive or negative, but should satisfy some growth condition. Here we don't need the growth condition, but we need u to be non-negative. Okay, so you understand that these two theorems are not actually special case of either of these. Okay, but they have different applicabilities. Next, let u be again the C12 function, and del u del t is equal to half del t u del x2, and here instead of 0 I am writing f of x. Okay, that u of t y as t tends to 0, y tends to x, u of t y goes to f of x, okay, for all x in R. So, if that is the case, okay, then u is equal to minus infinity f of y, this is the representation. Then u, this, I mean the solution u has this representation. It can be written in terms of integration of f and integrated using that probability density function p, okay, is the only non-negative solution to the problem. So, here we got the uniqueness that the solution, okay, it has only one single solution, and that solution is written in terms of this. So, this is in other words like conditional expectation of f of wt given w0 is equal to x, correct. So, this representation is there. However, this does not say that the problem has no other classical solution, okay. So, here so far non-negative solution you are talking about, okay, but it can have positive negative like that term classical solution, okay. So, that as I told that, okay, this is not a special case of Tikhonov's theorem, these have two different applicability. So, if you want I mean if you have this bounded condition in addition, then you can talk about unique solution, okay.